Okay, let's get on to the block I/O layer. All right, my pen. All right. Block devices are hardware devices distinguished by the random, that is, not necessarily sequential access of fixed size chunks of data. The fixed size chunks of data are called blocks. The most common block device is a hard disk, but many other block devices exist, such as floppy drives, Blu ray readers, and flash memory. Notice how these are all devices on which you mount a file system. File systems are the lingua franca of block devices. Okay? So basically, the communications for block devices. That's what file systems are. And the other basic type of device is a character device. Character devices or char devices are accessed as a stream of sequential data, one byte after another. Example character devices are serial ports and keyboards. If the hardware device is accessed as a stream of data, it is implemented as a character device. On the other hand, if the device is accessed randomly, non-sequentially, it is a block device. So, uh, I guess character devices are streams of data, one byte after another, and then block devices can move randomly across its like universe, I guess. So the difference comes down to whether the device accesses data randomly. So basically, in other words, whether the device can seek to one position from another. So that's what it means. A block device can seek from one position to another versus a character device. You have no control for that. As an example, consider the keyboard. As a driver, the keyboard provides a stream of data. If you type wolf, the keyboard driver returns a stream with those four letters in exactly that order. Reading the letters out of order or reading any letter but the next one in the stream makes little sense. The keyboard driver is thus a char device. The device provides a stream of characters that the user types onto the keyboard. Reading from the keyboard returns a stream first with W, then O, then L, and ultimately F. When no keystrokes are waiting, the stream is empty. A hard drive, conversely, is quite different. The hard drive's driver might ask to read the contents of one arbitrary block and read the contents of a different block. The blocks need not be consecutive. The hard disk's data is accessed randomly and not as a stream. Therefore, the hard disk is a block device. I think also one thing is that network devices are like this is just like a fun fact from what I've read before. Network devices like network cards are not exactly block devices or character devices. I think they're like their own different types, even though it might seem like a network card could be a character device since you can't really access um, it randomly or access the data randomly. But I think it's probably more like a temporal type of thing. Uh, Managing block devices in the kernel requires more care, preparation, and work than managing character devices. Character devices have only one position, the current one, whereas block devices must be able to navigate back and forth between any location on the media. Okay, again, character devices only have one position you can read. So basically one byte at a time, literally. So you read a byte, and then you expect when you read again, it should be something different. Versus block devices, you can actually jump from one place to another. We had to like really reiterate that concept. Indeed, the kernel does not have to provide an entire subsystem dedicated to the management of character devices, but block devices receive exactly that. Such a subsystem is a necessity partly because of the complexity of block devices. A large reason, however, for such extensive support is that block devices are quite performance sensitive. Getting every last drop out of your hard disk is much more important than squeezing an extra percent of speed out of your keyboard. Furthermore, as you will see, the complexity of block devices provide a lot of room for such optimizations. The topic of this chapter is how the kernel manages block devices and their requests. This part of the kernel is known as the block I/O layer. Interestingly, revamping the block I/O layer was the primary goal for the 2.5 development kernel. This chapter covers all new block I/O layer in the 2.6 kernel. Anatomy of a block device. The smallest addressable unit on a block device is a sector. Sectors come in various powers of 2, but 512 bytes is the most common size. The sector size is a physical property of the device, and the sector is the fundamental unit of all block devices. The device cannot address or operate on a unit smaller than a sector, although many block devices can operate on multiple sectors at a time. Most block devices have 512 byte sectors, although other sizes are common. For example, many CD-ROM disks have 2 kilobyte sectors. So sectors are the smallest unit on the device. The smallest physical property of the device is the sector. Okay, so software has different goals and therefore imposes its own smallest logically addressable unit, which is a block. The block is an abstraction of the file systems. File systems can be accessed only in multiples of a block. Although the physical device is addressable at the sector level, the kernel performs all disk operations in terms of blocks. Okay, so let's do this. Excalidraw. So we have block devices. So hardware communications where the block device operates on sectors. And they can go from, I think it was like 512 bytes to, 2 kilobytes, depending on the device. And this is device specific. Whereas in software, we don't deal with sectors, we deal with blocks. Okay, let's read. Because the device's smallest addressable unit is a sector, the block size can be no smaller than the sector and must be a multiple of the sector. Therefore, the kernel, as with hardware and the sector, needs the block to be a power of 2. The kernel also requires that a block be no larger than the page size. Okay, so it can't be bigger than the page size. Okay, therefore, block sizes are a power of 2 multiple of the sector size and not greater than the page size. So important is that in software, if you have a 32-bit system, your block can either be 512 bytes, which is what a sector is, could be sector depending on the device, all the way up to 4 kilobytes. Versus on the 64-bit system, you can have a 512 byte sectors all the way up to 8 kilobytes, which is, these are just the page size, right? Page size. So, and that makes sense because in virtual memory, you're moving pages in and out, so you'll need to be able to address blocks in some sort of multiple up to that page size. So blocks is the fundamental unit for block I/O, whereas in hardware, it is sectors and it's dependent on the device. Whereas blocks is just an abstraction on top of the sectors, and this, I guess, is configurable anywhere from 512 bytes, which is 0.5 KB, all the way up to, I think it should be like KIB. Yeah, KIB to 4 kilobytes. Okay, so common block sizes are 512 bytes, 1 kilobyte, and 4 kilobytes. Somewhat confusingly, some people refer to sectors and blocks with different names. Sectors, the smallest addressable unit to the device, are sometimes called hard sectors or device blocks. Meanwhile, blocks with the smallest addressable unit to the file system are sometimes referred to as file system blocks or I/O blocks. This chapter continues to call the two notions sectors and blocks, but you should keep these other terms in mind. figure 14.1 is a diagram of the relationship between sectors and buffers. Other terminology, at least with respect to hard disks, is common. Terms such as clusters, cylinders, and heads. Those notions are specific only to certain block devices and for the most part are invisible to user space software. The reason that the sector is important, okay, to the kernel is because all device I/O must be done in units of sectors. In turn, the higher level concept used by the kernel, blocks, is built on top of sectors. Okay. So now for kernel, we have sectors, and then we have, actually that's not even good. Let's do it better. Kernel. Okay, so then we'll have sector, 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 sector. Then we'll have blocks on top. So this is the abstraction. We overlay block on top of sector. So that's how I'm seeing it. Okay. All right. It's the same diagram. It's just I think my two-dimensional one might be easier to understand. Okay. So yeah. So mapping of sectors to blocks with the hard disk. Anyway. Buffer and buffer heads. When a block is stored in memory, say after a read or pending a write, it is stored in a buffer. Each buffer is associated with exactly one block. The buffer serves as the object that represents a disk block in memory. Recall that a block is composed of one or more sectors but is no more than a page in size. Therefore, a single page can hold one or more blocks in memory. Because the kernel requires some associated control information to accompany the data, such as from which block device and which specific block the buffer is, each buffer is associated with a descriptor. Okay, so a block is composed of one or more sectors, but is not bigger than the page size. Okay, so a single page can potentially hold one, right? If a block is as big as a page, or more blocks in memory. Because kernel requires some associated like metadata to accompany that data, okay, each buffer is associated with a descriptor. The descriptor is called a buffer head and is of type struct buffer head. The buffer head structure holds all the information that the kernel needs to manipulate buffers and is defined in Linux bufferhead.h. Let's take a look at this structure with comments describing each field. So here it is. Not going to go too much into it, but here's the associated page with the buffer head. And I guess it could potentially contain multiple blocks. So basically, we have the pointer to map to the data within the page versus this is the pointer to that page. The associate block device, starting block number. Okay, sure. The B state field specifies the state of this particular buffer. It can be one or more of the flags in table 14.1. The legal flags are stored in BH state bits enumeration, which is defined in Linux bufferhead.h. So here are all the flags. BH up to date, buffer contains valid data. BH dirty means it's dirty. The contents of the buffer are newer than the contents on the block on the disk, and therefore the buffer must eventually be written back to disk. Oh yeah, so the buffer is basically holding like the most present state of what the disk should reflect after some sort of flush. BH lock, buffer is undergoing disk I/O and is locked to prevent concurrent access. BH rec, the buffer is involved in an I/O request. BH mapped, the buffer is a valid buffer mapped on this block. BH new, buffer is newly mapped. BH async read, buffer is undergoing async read via end buffer async read. Async write is the opposite, so asynchronous write via end buffer async write. BH delay, buffer does not have an associated on this block. Okay. BH boundary, buffer forms a boundary of contiguous blocks. the next block is discontinuous. The buffer forms the boundary of contiguous blocks. The next block is discontinuous. Oh, so it's the boundary. Okay. BH write EIO. Buffer incurred an IO error. So error IO. BH ordered is an ordered write. BH E op not supported. I bet error not supported. Yep. Unwritten space for the buffer has been allocated on disk, but the actual data has not yet been written out. And BH quiet suppresses errors for this buffer. Probably a bad idea. Okay, so the BH state bits enumeration also contains as the last value in the list of a BH private start flag. This is not a valid state flag, but instead corresponds to the first usable bit of which other code can make use. All bit values equal to and greater than BH private start are not used by the block IO layer proper, so these bits are safe to use. By individual drivers who want to store information in the B state field. Wait. So these bits are safe to use by individual drivers who want to store information in the B state field. Okay. Drivers as in like hardware drivers. I was confused by that. Okay, so drivers can base the bit values of their internal flags off this flag and rest assured that they are not encroaching on an official bit used by the block IO layer. So the B count field is the buffer's usage count. The value is incremented and decremented by two inline functions, both of which defined in Linux buffer head. So I'm guessing this is like the number of devices or processes, maybe like making access to the device or actually trying to get to the device by the way of the buffer. So you'll have an increment, and then you also have a decrement. Okay, so put, get. Before manipulating a buffer head, you must increment its reference count via getBH to ensure that the buffer head is not deallocated from under you. When finished with the buffer head, decrement the reference count via putBH. The physical block on disk to which the given buffer corresponds is the block number logical block on block number NR, the one that we saw from the struct definition. Logical block on the block device described by bdev. The physical page in memory to which a given buffer corresponds is the page pointed to by bpage. More specifically, bdata is a pointer directly to the block that exists somewhere in bpage, which is b size bytes in length. Therefore, the block is located in memory starting at address bdata and ending at address bdata b size. So that's the size of the block, the total size. Makes sense. So these are pointers. The purpose of a buffer head is to describe this mapping between the on-disk block and physical in-memory buffer, which is a sequence of bytes on a specific page. Acting as a descriptor of this buffer to block mapping is the data structure's only role in the kernel. Before the 2.6 kernel, the buffer head was much more important. It was a much more important data structure. It was the unit of I/O in the kernel. Not only did the buffer head describe the disk block to physical page mapping, but it also acted as the container used for all block I/O. This had two primary problems. First, the buffer head was a large and unwieldy data structure, and it has shrunken a bit nowadays. And it was neither clean nor simple to manipulate data in terms of the buffer heads. Instead, the kernel prefers to work in terms of pages, which are simple and enable for greater performance. A large buffer head describing each individual buffer, which might be smaller than a page, was inefficient. Consequently, in the 2.6 kernel, much work has gone into making the kernel work directly with pages and address spaces instead of buffers. Much work directly with pages and address instead of buffers. Okay, so another layer is probably on top of this is going to be like pages. Or pages on top of buffers, I'm guessing. Buffers, okay. And then pages. Okay. Some of this work is discussed in Chapter 16, the page cache and page write back, where the address space structure and PD flush daemons are discussed. The second issue with buffer heads is that they describe only a single buffer. When used as a container for all I/O operations, the buffer head forces the kernel to break up potentially large block I/O operations, say write, into multiple buffer head structures. Well, that's a lot of work. This results in needless overhead and space consumption. As a result, the primary goal of the 2.5 development kernel was to introduce a new flexible and lightweight container for block I/O operations. The result is the BIO or BIO structure, which is discussed in the next section. Okay, the BIO or BIO structure. So the basic container for block I/O within the kernel is the BIO structure, which is defined in Linux/bio.h. This structure represents block I/O operations that are in flight or active as a list of segments. A segment is a chunk of a buffer that is contiguous in memory. Thus, individual buffers need not to be contiguous in memory, by allowing the buffers to be described in chunks. The BIO structure provides the capability for the kernel to perform block I/O operations of even a single buffer from multiple locations in memory. Vector I/O such as this is called scatter-gather I/O. Okay? So by allowing buffers to be described in chunks, the BIO structure provides the capability for the kernel to perform block I/O operations of even a single buffer from multiple locations in memory. Okay? Alright, so vector I/O. This is called vector I/O, scatter-gather I/O. Here's a struct bio defined in Linux/bio.h with the comments added to each field. Okay. Lots of stuff. Basically I/O count. Where is... Oh, here, the bio-vect list. Okay. So that's probably interesting here. What else? What else we have? I guess we'll wait. We'll read this thing. Okay, so the primary purpose of a BIO structure is to represent an in-flight block I/O operation. So in-flight block I/O operations are basically represented as BIO structures. To this end, the majority of the fields in this structure are housekeeping related. Okay, that's why I'm lost. The most important fields are the BI IOVEC, BI VCNT, and BI IDX. Okay? Figure 14.2 shows the relationships between the BIO structure and its friends. So BIO structure points to a list of these BIOVECs where they all have a page associated with them. Okay. Okay. So IO vectors. The BI IOVEC field points to an array of BIOVEC structures. These structures are used as lists of individual segments in the specific block I/O operation. Each BIOVEC is treated as a vector of the form page offset len, which represents a specific segment, the physical page on which it lies, the location of the block as an offset into the page, and the length of the block starting from that given offset. The full array of these vectors describes the entire buffer. The BIOVEC structure is defined in Linux/bio.h. So you'll have the pointer to the page where the buffer lives, and then the length of the buffer, and then the offset of where this buffer is within that page. Okay? In each given block I/O operations, there are BI, VCNT vectors in the BIOVEC array. Starting with the BIO vec. Okay? As the block I/O operation is carried out, the BI IDX field is used to point to the current index into the array. In summary, each block I/O request is represented by a BIO structure. Each request is composed of one or more blocks, which are stored in an array of BIOVEC structures. And these structures act as vectors and describe each segment's location in the physical page in memory. The first segment in the I/O operation is pointed to by BIOVEC. Each additional segment follows after the first for the total of BIVCNT segments in the list. As the block I/O layer submits segments in the request, the BI IDX field is updated to point to the current segment. The BI IDX field is used to point to the current BIOVEC in the list, which helps the block I/O layer keep track of partially completed block I/O operations. A more important usage, however, is to allow the splitting of biostructures. With this feature, drivers implementing RAID, or redundant array of inexpensive disks, right, can take a single biostructure and initially intended for a single device and split it among the multiple hard drives in the RAID array. All the RAID driver needs to do is copy the biostructure and update the BIDX field to point to where the individual drive should start its operation. The biostructure maintains a usage count in the BICNT field. When this field reaches 0, the structure is destroyed and the backing memory is freed. The following two functions manage the usage counters for you. Okay, bioget, bioput. So the former increments the usage count. So it's the same thing as like the buffer thing again. Whereas the latter decrements the usage count, and if the count reaches 0, destroys the biostructure. Before manipulating an in-flight biostructure, be sure to increment its usage count to make sure that it does not complete and deallocate out from under you. When you finish, decrement the usage count in turn. Finally, the BI private field is a private field for the owner, that is the creator of the structure. As a rule, you can read or write this field only if you allocated the biostructure. Okay. The old versus the new. The difference between buffer heads and the new biostructure is important. The biostructure represents an I/O operation, which may include one or more pages in memory. So in-flight I/O, that's what biostructure is. On the other hand, the buffer head structure represents a single buffer, which describes a single block on the disk. So it's more static, not in-flight. Because buffer heads are tied to a single disk block in a single page, the buffer heads result in unnecessary dividing, okay, of requests into block-sized chunks, only to later reassemble them. Because the biostructure is lightweight, it can describe discontinuous blocks and does not unnecessarily split I/O operations. Switching from struct buffer head to struct bio provided other benefits as well. First, the biostructure can easily represent high memory because the struct bio deals with only physical pages and not direct pointers. And then the biostructure can represent both normal page I/O and direct I/O, which is I/O operations that do not go through the page cache. And we'll learn that in chapter 16, the page cache and page write back, okay? And then the biostructure makes it easy to perform scatter, gather, vectored block I/O operations with the data involved in the operation originating from multiple physical pages. The biostructure is much more lightweight than a buffer head because it contains only the minimum information needed to represent block I/O operation and not unnecessary information related to the buffer itself. Okay. The concept of buffer heads is still required. However, buffer heads function as descriptors mapping disk blocks to pages. Okay, buffer heads function as descriptors mapping disk blocks to pages. There we go. The biostructure does not contain any information about the state of a buffer. It simply is an array of vectors describing one or more segments of data for a single block I/O operation and plus related information. So it doesn't really perform anything. It's just describing an I/O operation. In the current setup, the buffer head structure is still needed to contain information about buffers, while the biostructure describes in-flight I/O. Keeping the two structures separate enables each to remain as small as possible. Okay, request queues. Block devices maintain request queues to store their pending block I/O requests. The request queue is represented by the request queue structure and is defined in Linux/blk.h. The request queue contains a doubly linked list of requests and associated control information. Requests are added to the queue by higher level code in the kernel, such as file systems. As long as the request queue is non-empty, the block device driver associated with the queue grabs the request from the head of the queue and submits it to its associated block device. Each item in the queue's request list is a single request and of type struct request. Individual requests on the queue are represented by struct request, which is also defined in Linux/blkdev.h. Each request can be composed of one of more than one biostructure because individual requests can operate on multiple consecutive disk blocks. Note that although the blocks on the disk must be adjacent, the blocks in memory need not be. Each BIOS structure can describe multiple segments. Recall segments are contiguous chunks of block in memory. Okay? And the request can be composed of multiple BIOS structures. Okay. Let's see how much time we have. Only 30 minutes in. All right. Okay. IO schedulers. Simply sending out requests to the block devices in the order that the kernel issues them as soon as it sees them results in poor performance. One of the slowest operations in a modern computer is disk seeks. Each seek positioning the hard disk heads at the location of a specific block takes many milliseconds. Yeah, nowadays we have SSDs, so we take that for granted. Minimizing seeks is absolutely crucial to the system's performance. Therefore, the kernel does not issue block I/O requests to the disk in the order they are received or as soon as they are received. Instead, it performs operations called merging and sorting to greatly improve the performance of the system as a whole. The subsystem of the kernel that performs these operations is called the I/O scheduler. Okay, so you just can't throw things to the device. You had to have some scheduling going on to optimize that, throughput. Basically all those IO requests that go to the device, they had to kind of be smartly arranged so that you're constantly not moving back and forth between the disk. Anyway, the IO scheduler divides the resource of disk IO among the pending block IO requests in the system. It does this through the merging and sorting of pending requests in the request queue. The IO scheduler is not to be confused with the process scheduler, see Chapter 4, Process Scheduling, which divides the resource of the processor among the processes on the system. The two subsystems are similar in nature but not the same. Both the process scheduler and the IO scheduler virtualize a resource among multiple objects. In the case of the process scheduler, the process is virtualized and shared among the processes on the system. This provides the illusion of virtualization inherent in a multitasking and time-sharing operating system such as any Unix. On the other hand, the IO scheduler virtualizes block devices among multiple outstanding block requests. This is done to minimize disk seeks and ensure optimum disk performance. The job of an IO scheduler. An IO scheduler works by managing a block device's request queue. It decides the order of requests in the queue and at what time each request is dispatched to the block device. It manages the request queue with the goal of reducing seeks, which results in greater global throughput. The modifier global here is important. An IO scheduler very openly is unfair to some requests at the expense of improving the overall performance of the system. IO schedulers perform two primary actions to minimize seeks. First, merging and sorting. Okay, merging is the coalescing of two or more requests into one. Two or more requests into one. Consider an example request that's submitted to the queue by a file system, say to read a chunk of data from a file. At this point, of course, everything occurs in terms of sectors and blocks and not files, but presume that the requested blocks originate from that chunk of a file. If a request is already in the queue to read from an adjacent sector on the disk, for example, an earlier chunk of the same file, the two requests can be merged into a single request operating on one or more adjacent on-disk sectors. By merging requests, the IO scheduler reduces the overhead of multiple requests down to a single request. More important, only a single command needs to be issued to the disk and servicing the multiple requests can be done without seeking. Consequently, it's raining really hard outside. Okay. Consequently, merging requests reduces overhead and minimizes seeks. Now assume your fictional read request is submitted to the request queue, but there is no read request to an adjacent sector. You therefore cannot merge this request with any other request. Now you could simply stick this request onto the tail of the queue. But what if there are other requests to a similar location on the disk? Would it not make sense to insert this new request into the queue at a spot near other requests operating on physically near sectors? In fact, IO schedulers do exactly this. The entire request queue is kept sorted. sector-wise so that all seeking activity along the queue moves as much as possible sequentially over the sectors of the hard disk. The goal is not to just minimize each individual seek, but to minimize all seeking by keeping the disk head moving in a straight line. This is similar to the algorithm employed in elevators. Elevators do not jump all over wildly from floor to floor. Instead, they try to move gracefully in a single direction. When the final floor is reached in one direction, the elevator can reverse course and move in the other direction. Because of this similarity, I/O schedulers, or sometimes just their sorting algorithm, are called elevators. The Linus elevator. Now let's look at some real-life I/O schedulers. The first I/O scheduler is called the Linus elevator. Yes, Linus has an elevator named after him. It was a default I/O scheduler in 2.4. In 2.6, it was replaced by the following I/O schedulers that we will look at. However, because this elevator is simpler than the subsequent ones while performing many of the same functions, it serves as an excellent introduction. The Linus elevator performs both merging and sorting. When a request is added to the queue, it is first checked against every other pending request to see whether it is a possible candidate for merging. The Linus elevator I/O scheduler performs both front and back merging. The type of merging performed depends on the location of the existing adjacent request. If the new request immediately precedes an existing request, it is front merged. Okay? Conversely, if the new request immediately precedes an existing request, it is back merged. Because of the way files are laid out, usually by increasing sector number, and the I/O operations performed in a typical workload, that is, data is normally read from start to finish and not in reverse, front merging is rare compared to back merging. Nonetheless, the Linus elevator checks for and performs both types of merge. If the merge attempt fails, a possible insertion point in the queue, a location in the queue where the new request fits sector-wise between existing requests, so the best location in that queue, the best index, is then sought. If one is found, the new request is inserted there. If a suitable location is not found, the request is added to the tail of the queue. Additionally, if an existing request is found in the queue that is older than the predefined threshold, okay, the new request is added to the tail of the queue even if it can be inserted. It can be insertion sorted elsewhere. This prevents many requests to nearby on-disk locations from indefinitely starving requests to other locations on the disk. Unfortunately, this age check is not efficient. It does not provide any real attempt to service requests in a given time frame. It merely stops insertion sorting requests after a suitable delay. This improves latency but can still lead to request starvation, which was the big must fix of the 2.4 I/O scheduler. Okay. So in summary, when a request is added to the queue, 4 operations are possible. In order they are: if a request to an adjacent on-disk sector is in the queue, the existing request and the new request merge into one single request. Make sense? If a request in the queue is sufficiently old, the new request is inserted at the tail of the queue to prevent starvation of the older requests. If a suitable location sector-wise is in the queue, the new request is inserted there. This keeps the queue sorted by the physical location on disk. Finally, if no such suitable insertion point exists, the request is inserted at the tail of the queue. The Linus elevator is implemented in blockelevator.c. Okay. So the deadline I/O scheduler. The deadline I/O scheduler sought to prevent the starvation caused by the Linus elevator. In the interest of minimizing seeks, heavy disk I/O operations to one area of the disk can indefinitely starve request operations to another part of the disk. Indeed, a stream of requests to the same area of the disk can result in other far-off requests never being serviced. This starvation is unfair. Worse, the general issue of request starvation introduces a specific instance of the problem known as write-starving reads. Write operations, can usually be committed to disk whenever the kernel gets around to them, entirely asynchronous with respect to the submitting application. Read operations are quite different. Normally, when an application submits a read request, the application blocks until the request is fulfilled. That is, read requests occur synchronously with respect to the submitting application. Although system response is largely unaffected by write latency, the time required to commit a write request, Read latency, the time required to commit a read request, is important because it's blocking. With write latency has little bearing on application performance, but an application must wait twiddling its thumbs for the completion of each read request. Consequently, read latency is important to the performance of the system. Compounding the problem, read requests tend to be dependent on each other. For example, consider the reading of large number of files. Each read occurs in small buffered chunks. The application does not start reading the next chunk, or the next file for that matter, until the previous chunk is read from disk and returned to the application. Worse, both read and write operations require the reading of various metadata, such as inodes. Reading these blocks off the disk further serializes I/O. Consequently, if each read request is individually starved, the total delay to such applications compounds and can grow enormous. Recognizing that the asynchrony and interdependency of read requests results in a much stronger bearing of read latency on the performance of the system. The deadline I/O scheduler implements several features to ensure that the request starvation in general and read starvation in specific is minimized. Note that reducing request starvation comes at a cost to global throughput. Even the Linus elevator makes this compromise, albeit in a much milder manner. The Linus elevator could provide better overall throughput via a greater minimization of seeks if it always inserted requests into the queue sector-wise and never checked for old requests and reverted to insertion at the tail of the queue. Although minimizing seeks is important, indefinite starvation is not good either. The deadline I/O scheduler therefore works harder to limit starvation while still providing good global throughput. Make no mistake, it is a tough act to provide request fairness, yet maximize global throughput. In the deadline I/O scheduler, each request is associated with an expiration time, hence deadline. By default, the expiration time is 500 milliseconds in the future for read requests and 5 seconds for the future for write requests. The deadline I/O scheduler operates similarly to the Linus elevator in that it maintains a request queue sorted by physical location on disk. It calls this queue the sorted queue. When a new request is submitted to the sorted queue, the deadline I/O scheduler performs merging and insertion like the Linus elevator. The deadline I/O scheduler also inserts the request into the second queue that depends on that type of request. Okay, read requests are sorted into a special read FIFO queue. So two types of queues now. And write requests are inserted into a special write FIFO queue. Although the normal queue is sorted on disk by on disk sector, these queues are kept FIFO. Okay, effectively they are sorted by time. Okay, so I say come in. That's how they're arranged. Consequently, new requests are always added to the tail of the queue. Under normal operation, the deadline I/O scheduler pulls requests from the head of the sorted queue into the dispatch queue. The dispatch queue is then fed to the disk drive. This results in minimal seeks. If the request at the head of either the write FIFO queue or the read FIFO queue expires, that is, the current time becomes greater than the expiration time associated with the request, the deadline I/O scheduler then begins servicing requests from the FIFO queue. In this manner, the deadline I/O scheduler attempts to ensure that no request is outstanding longer than its expiration time. So you have 1, 2, 3 queues here, one for reads, one for writes, and then a sorted one, and they all go to the fourth final queue that will actually go to disk. Note that the deadline I/O scheduler does not make any strict guarantees over request latency. It is capable, however, of generally committing requests on or before their expiration. This prevents request starvation because read requests are given a substantially smaller expiration time than write requests. The deadline I/O scheduler also works to ensure that the write requests do not starve read requests. This preference toward read requests provides minimized read latency. The deadline I/O scheduler lives in block/deadline IO schedule.c. The anticipatory I/O scheduler. Although the deadline I/O scheduler does a great job minimizing read latency, it does so at the expense of global throughput. Consider a system undergoing heavy write activity. Every time a read request is submitted, the I/O scheduler quickly rushes to handle the read request. This results in the disk seeking over to where the read is, performing the read operation, and then seeking back to continue the ongoing write operation, repeating this little charade for each read request. The preference towards read requests is a good thing, but the resulting pair of seeks, one to the location of the read request and another back to the ongoing write, is detrimental to global disk throughput. The anticipatory I/O scheduler aims to continue to provide excellent read latency, but also provide excellent global throughput. Okay. So first, the anticipatory I/O scheduler starts with the deadline I/O scheduler as its base. Cool, sort of like relatives. Therefore, it is not entirely different. The anticipatory I/O scheduler implements 3 queues plus dispatch queue and the expirations for each request. Wait. Oh, it's the same thing. Okay. Just like the deadline I/O scheduler, the major change is the addition of the anticipation heuristic, so the algorithm. The anticipatory I/O scheduler attempts to minimize the seek storm that accompanies read requests issued during other disk I/O activity. When a read request is issued, it is handled as usual when within its usual expiration period. After the request is submitted, however, the anticipatory I/O scheduler does not immediately seek back to and return to handling other requests. Instead, it does absolutely nothing for a few milliseconds. The actual value is configurable. By default, it is 6 milliseconds. In those few milliseconds, there is a good chance that the application will submit another read request. Any requests issued to an adjacent area of the disk are immediately handled. After the waiting period elapses, the anticipatory I/O scheduler seeks back to where it left off and continues handling the previous requests. It is important to note that the few milliseconds spent in anticipation for more requests are well worth it if they minimize even a modest percentage of the back and forth seeking that results from the servicing of read requests during other heavy requests. If an adjacent I/O request is issued within the waiting period, the I/O scheduler just saved a pair of seeks. As more and more reads are issued to the same area of disk, many more seeks are prevented. Of course, if no activity occurs within the waiting period, the anticipatory I/O scheduler loses and a few milliseconds are wasted. The key to reaping maximum benefit from the anticipatory I/O scheduler is correctly anticipating the actions of applications and file system. This is done via a set of statistics and associated heuristics. The anticipatory I/O scheduler keeps track of per process statistics pertaining to the block I/O and habits in hopes of correctly anticipating the actions of applications. With a sufficiently high percentage of correct anticipations, the anticipatory I/O scheduler can greatly reduce the penalty of seeking to service read requests, so minimizing the spinning of the disk, while still providing the attention to such requests that the system response requires. This enables the anticipatory I/O scheduler to minimize read latency while also minimizing the number of duration of seeks. This results in low system latency and high system throughput. The anticipatory I/O scheduler lives in the file block/IO as ioschedule.c in the kernel source tree. It performs well in most workloads. It is ideal for servers, although it performs poorly on certain uncommon but critical workloads involving seek-happy databases. So bad on databases. Is this the last one? Oh. Okay, can we finish it? Let's see. Nah, I'll finish it next time. Yeah.